Welcome back, everyone, to the deep dive. Sometimes those topics from school, they kind of sneak up on you later in life.
Yeah.
And you find yourself thinking, wait a minute, I learned about that once, but how does it actually apply in the real world?
Mm-hmm. Mm.
Well, today's deep dive is going to tackle one of those topics. We're going back to algebra class.
Whoa, back to school.
Yes, back to school, but don't worry, no pop quizzes here. We're going to explore the world of linear equations in two variables.
Okay.
And I know what you might be thinking, linear equations, not exactly the most thrilling subject, but trust me, there's more to these equations than meets the eye.
I agree.
We've got some really cool source material to guide us, and our mission today is to go beyond the textbook definitions and really unlock the power of these equations.
Yeah, we're going to see how they can help us understand relationships between different things in the world around us.
Exactly. By the end of this deep dive, you'll have those aha moments where you see these equations playing out in your everyday life, whether it's Akila having a blast at the village fair, Champa deciding what clothes to buy, or even just figuring out how much that taxi ride is going to cost you.
Those are great examples.
So, are you ready to dive in?
I am. I'm ready. Let's get started.
Okay, let's start with the basics. What exactly is a linear equation in two variables? I mean, what does that even mean?
So imagine a straight line on a graph. That's essentially what a linear equation represents. And when we say two variables, we mean it has two unknown quantities, usually represented by the letters x and y.
Okay, like x could be the number of rides Akila goes on at the fair, and y could be the amount of money she spends, something like that.
Exactly. And the equation connects those two variables in a specific way. For example, it could tell you that each ride costs a certain amount, and then there's maybe an entry fee.
Got it. So one equation, one straight line. But today, we're talking about pairs of linear equations.
Right. We're dealing with two of these equations at the same time.
So two lines on the same graph. What happens then?
Well, that's where things get interesting. When you put two lines on the same graph, there are only three ways they can interact with each other.
Okay, tell me about those three possibilities.
The first possibility is that the two lines intersect each other. They cross at one specific point.
Like two roads crossing at an intersection.
Precisely. And that point where they intersect is the key.
How so?
Well, that point represents the one and only solution that satisfies both equations simultaneously. In other words, it's the single set of values for x and y that makes both equations true. We call this a consistent pair of equations because there's a solution that works for both.
So it's like finding that sweet spot where two different conditions are met at the same time. Is there an example of this in the material?
Yeah, there is. Example 1 gives us two equations, x plus 3y equals 6 and 2x minus 3y equals 12. And if you graph those equations, you'll see that they intersect at the point 6.
Meaning that x equals 6 and y equals 0 is the unique solution that fits both those equations.
Right. And, in real-world terms, it could be something like, okay, Akila bought 6 ride tickets and spent 0 rupees on games.
Makes sense. So one intersection, one specific answer. What's the next possibility?
The second possibility is that the two lines are parallel to each other.
Okay, like train tracks that run side by side but never meet.
Exactly. They just keep going in the same direction, always maintaining the same distance between them.
And what does that mean in terms of solutions?
Well, if the lines are parallel, they never intersect. So there's no point that lies on both lines, which means there's no single solution that works for both equations. We call this an inconsistent pair of equations.
No meeting point, no shared solution. Makes sense. Got an example of this?
Sure. Example 3 gives us x plus 2y minus 4 equals 0 and 2x plus 4y minus 12 equals 0. And those two lines, they're parallel.
So no matter what values you plug in for x and y, you'll never find a combination that satisfies both equations at the same time.
Exactly. It suggests that those two conditions represented by the equations, they just can't coexist.
They're fundamentally incompatible, like oil and water. All right, so we've got intersecting lines with one solution, parallel lines with no solution. What's the third possibility?
The third possibility is kind of unique. The two lines could be coincident.
Coincident.
Coincident lines. It means they're basically the same line. They lie right on top of each other.
Ah, so every point on one line is also a point on the other line.
You got it. This means there are infinitely many points that they share, which translates to infinitely many solutions that satisfy both equations. It's like having two equations that say the same thing, just written in different ways.
Hmm.
We call this a dependent pair of linear equation.
Dependent, because one equation is basically a copycat of the other.
Right, and although there's not one single solution, it's still considered a consistent pair because solutions do exist, just not a unique one.
So lots of answers, but still a valid scenario. Got an example of this.
Example 2 showcases this perfectly. It gives us 5x minus 8y plus 1 equals 0, and 3x minus 245y plus 35 equals 0.
No, those look different.
They do, but if you look closely, you'll see that the second equation is just a multiple of the first equation. If you simplify it, they're essentially the same line.
Ah, I see. So if we graph those, they'd overlap completely, and every point on that line would be a solution.
Exactly.
Okay, so to recap the visuals, intersecting lines give us one solution, parallel lines give us no solution, and coincident lines give us infinite solutions. But I remember from the material that there's a way to figure out which of these scenarios we're dealing with without even having to draw the lines. Something about comparing the numbers in the equations.
Yeah, you're right. It's all about looking at the coefficients. Those are the numbers in front of x and y and also the constant term.
Right, the coefficients and the constant terms. Tell me more about that.
So when you have two linear equations written in their standard form, like a arrows plus b arrow plus c arrow equals 0 for the first equation, and a arrow plus b arrow plus c arrows equals 0 for the second one, you can figure out how the lines will behave just by comparing the ratios of those coefficients.
Okay, so we're talking about the ratios like a arrow over b and c over d.
Right, those three ratios hold the key. Now, if the ratio of a arrow over arrow is not equal to the ratio of b over bo, then we know the lines will intersect.
So if those first two ratios are different, bam, we're guaranteed to have one solution.
Precisely. That's because different ratios mean the lines have different slopes, so they're bound to cross somewhere.
It's like two cars traveling at different speeds in different directions. They got to meet at some point.
Hmm.
Okay, what about the other cases?
Well, if all three ratios are equal, a over a or over b equals c over c, then we're dealing with coincident lines.
Ah, so if all three ratios match, we know the lines are basically twins, and we'll have those infinite solutions.
Exactly. And finally, if the first two ratios are equal, a over a arrow equals b over b, but that ratio is not equal to c over c, then we know we have parallel lines.
So if the first two ratios match, but the third one's different, no solution, those lines will never meet.
Right. It's telling us the lines have the same slope because a over a arrow equals b over b.
Mm-hmm.
But they have different y-intercepts because that third ratio is different.
So they're like two cars traveling at the same speed, but starting from different places, never catching up to each other.
That's a great analogy. So just by comparing these three ratios, you can quickly determine whether you'll have one solution, no solution, or infinite solutions without even touching a graph.
That's a seriously handy trick. Now, we've covered the graphical method where we visualize the lines and this ratio method where we analyze the coefficients.
Right.
But our source material also talks about algebraic methods for solving these systems.
Yes.
Why do we need those if we can already figure things out graphically or by comparing ratios?
That's a good question. While those methods are great for understanding the nature of the solutions, they might not always give us the exact numerical answers, especially if the solution involves fractions or decimals.
Ah, so algebraic methods are like our precision tools, helping us get those pinpoint accurate solutions.
Exactly. And the first algebraic method we'll explore is the substitution method.
Substitution, okay. How does that work?
So the basic idea is to pick one of the equations and solve it for one variable in terms of the other variable.
So you're isolating one variable on one side of the equation.
Right, and then you take that expression and substitute it into the other equation. This basically eliminates one of the variables temporarily, allowing you to solve for the other one.
It's like a strategic swap, right?
Exactly. Once you've solved for one variable, you can plug that value back into either of the original equations to find the value of the other variable.
Got it. Is there an example that shows this in action?
Example 4 is a great illustration. We have 7x minus 15y equals 2 and x plus 2y equals 3. The example shows how to solve for x in the second equation,
Which gives us?
which gives us x equals 3 minus 2y.
Okay.
And then we substitute that expression for x in the first equation.
So instead of 7x, you'd have 7 times 3 minus 2y.
Exactly. And that lets you solve for y. And once you have the value of y, you plug it back into either equation to find x. In this example, you get a fractional solution, highlighting why algebraic methods can be more precise.
And the source material also mentions that the substitution method can reveal whether a system has no solution or infinite solutions.
Right, because during the substitution process, if you end up with a statement that's always false, like -4 equals 0, it means the original equations were inconsistent.
No solution, parallel lines.
Right. But if you get a statement that's always true, like 18 equals 18, it means there are infinitely many solutions.
Coincident lines.
Exactly.
Now, besides this example with the fractional solution, were there other real-world examples of using the substitution method?
Yes, there were. There was the problem about figuring out the ages of Aftab and his daughter, and another one about calculating the cost of pencils and erasers.
So the substitution method can be applied to all sorts of real-world problems, just like we talked about with those examples at the beginning.
Absolutely.
All right, substitution is one algebraic tool in our toolkit. What's the other one?
The other main algebraic method is the elimination method.
Elimination.
Okay, that sounds like we're getting rid of something.
We're strategically eliminating one of the variables. The idea is to manipulate the two equations so that when you add them or subtract them, one variable disappears.
Poof, it's gone. How do we do that?
The first step is often to multiply one or both of the equations by carefully chosen numbers to make the coefficients of either x or y the same in both equations.
So we're kind of rigging the game to get those coefficients to match. In a way, yes. And once the coefficients match, you either add the equations together if the matching coefficients have opposite signs, or you subtract one equation from the other if the matching coefficients have the same sign.
And that makes one of the variables vanish.
Exactly. And just like with substitution, you're left with a single equation with one variable. You solve for that variable, and then you substitute that value back into one of the original equations to find the value of the other variable.
It's like a two-step process: eliminate, then substitute. Do we have an example that walks us through this?
Example 8 is a great one. It deals with the ratio of incomes and expenditures of two people. They show you how to multiply the equations to get the y coefficients to match and then subtract to eliminate y.
So they manipulated the equations to make the y terms cancel each other out. Smart move.
Right. And the example also points out that this elimination method can also reveal inconsistent systems.
Where there's no solution.
Right. If during the elimination process you end up with a false statement, like 0 equals 9, that means the original equations were inconsistent.
Parallel lines, no solution.
Exactly. And just like with substitution, if you end up with a statement that's always true, it means there are infinitely many solutions.
Coincident lines.
Right.
Now, did the source material have any other interesting examples using the elimination method?
Yes, there was example 10, which was a word problem about a two-digit number.
That one was interesting because it actually led to two different possible pairs of equations.
Right. Depending on how you interpret the problem, you could set up the equations in two different ways, and each way would give you a valid solution.
It's like the problem had two different paths, each leading to a correct answer.
Precisely.
So we've got these two powerful algebraic methods, substitution and elimination, and they both can be applied to all sorts of real-world situations.
Yes.
Whether it's figuring out people's ages, the cost of items, or even understanding the relationship between income and spending, like in that last example.
Exactly. It's amazing how these seemingly abstract mathematical tools can be used to solve such a wide variety of practical problems.
It is. So let's take a step back and summarize what we've learned about pairs of linear equations. Basically, when you have two of these equations, you're trying to find the point or points that satisfy both equations at the same time. Graphically, it's all about how those two lines interact. Intersecting lines give us one unique solution, parallel lines give us no solution, and coincident lines give us infinitely many solutions.
And we saw that just by comparing the ratios of the coefficients in those equations, we can quickly determine which scenario we're dealing with without even drawing the line.
Exactly. And when we need those precise numerical solutions, especially when we're dealing with fractions or decimals, the algebraic methods, substitution and elimination, come to the rescue.
Right. And both of those methods also help us identify those special cases where there's no solution or infinite solutions.
Now, the source material also mentioned one last interesting tidbit. It said that sometimes you might come across problems that don't immediately look like linear equations.
Yeah.
But with a bit of clever manipulation, you can transform them into linear equations and then use all these techniques we've discussed.
Right, it's like turning a seemingly complex problem into something we know how to solve.
Exactly. So understanding pairs of linear equations is not just some theoretical concept from math class. It's a powerful tool for analyzing relationships between things that change together and for solving a surprisingly wide range of problems that we encounter in the real world.
Absolutely. And that brings us to a final thought for you to ponder. Think about your own life, your daily experiences, the things you observe around you. Can you identify other situations where you have two unknown quantities and two pieces of information that connect them? Maybe it's figuring out the best deal at the grocery store, or analyzing the relationship between exercise and calorie burn, or even predicting the growth of something over time. How could you represent those situations with a pair of linear equations? That's your challenge, to see those connections and apply this knowledge to your own little corner of the world.
That's a great challenge. And until our next deep dive, keep exploring, keep questioning, and keep those aha moments coming.
I love that.
Thanks for joining us.
Thanks for having me.